Today, we're quite pleased to have Dr. Krauss with me. He is an internationally known theoretical physicist, and I've wanted to talk to an internationally known theoretical physicist for about 30 years, whose research is focused on the interface between elementary particle physics and cosmology, including the fundamental structure of matter and the evolution of the universe. Among his numerous important and interesting scientific contributions was his 1995 proposal that most of the energy of the universe resided in empty space. During his career, Professor Krauss has held endowed professorships and distinguished research appointments at major institutions all over the world, including Harvard, Yale, and CERN. He is the author of 500 publications and 11 popular books, including the international bestsellers, The Physics of Star Trek, and A Universe from Nothing. His most recent book, The Physics of Climate Change, was released in February of this year, 2021. He won a major award from all three of the U.S. National Physics Societies, as well as the 2012 Public Service Award from the National Science Board for his contributions to the public understanding of science. He currently serves as president of the Origins Project Foundation, which celebrates science and culture by connecting scientists, artists, writers, and celebrities with the public through special events, online discussions, and unique travel opportunities. The foundation produces the Origins podcast, featuring dialogues with some of the most interesting people in the world, discussing issues that address the global challenges of the 21st century. Thank you very much for agreeing to talk to me today.
It's great to be with you virtually, Jordan.
Okay, so I have a question, and I'm going to jump right into it. I wrote a paper with a couple of my students. I was the final author on the paper. We tried to relate the experience of anxiety to a physical property, to entropy, which I suppose might be well defined as a physical property. And the idea was, and you tell me what you think of this as a physicist, if you would.
Okay.
The idea was that human beings are always trying to calculate a path from one point to another. And the length of the path is going to be proportionate in some sense to the energy used to undertake the task. Right? The longer the path, the more energy. Now, we generally take the path to something that we regard as valuable, and sources of energy, for example, are extremely valuable to us. And so that might be a shortcut to doing some work, because that's translatable into goods. Anyways, the cost of the voyage is an important consideration. And so whenever uncertainty is added to a plan, it becomes more and more difficult to formulate a map that lays out the trajectory appropriately. And you need a marker for that, a psychological marker. And so we assume that as the certainty of the path that you're going to take according to, given a particular reward, as the uncertainty of that increased, you experience this unease. And the unease was a marker of the increased complexity. And that would be the increased entropy, in some sense, of either of the landscape or of your representation of the landscape, or maybe of the disjunction between the two. So the first question I would have is I guess, first of all, was that a comprehensible explanation? And second of all, is that a reasonable way of construing entropy?
Well, yeah, okay. The answer is it's not unreasonable in a general sense. I'm very wary. I remember, when I was a kid, actually in Canada, and I remember I was always interested in science, but in university I took sociology, and I remember becoming fascinated at the time by various sociologists' attempts to define concepts, as if borrow from physics to define concepts. And I thought, wow, this is fascinating. As I got to know more physics, I became more wary of that application, because certain things that are well defined and appropriate in physical context become less well defined and perhaps have less utility. They sound good in a social science paper, but whether they actually allow predictive value is the important question.
Right, and so that's exactly why I'm asking the question. I'm aware of that problem, and that's why I wanted to see if there's some bedrock there.
Well, I think that I think you've got something in a sense that in physics, actually, in different contexts, there's trade-offs between energy and entropy, and they're well-defined thermodynamic quantities that are defined depending upon what you hold fixed and what you don't, and how the system evolves whether it evolved to a situation of least energy or least what's called free energy, which depends on, or enthalpy, which includes that entropy aspect, depends upon the specific circumstances of the physical situation. But that the complexity of a path is related to the entropy that is appropriate, because entropy really describes, and maybe it's probably useful for your listeners who may not be as aware of entropy as you are, that what it really describes is a macroscopic system has many different internal states it can be in. And entropy really just describes how many internal states a system has for a given macroscopic configuration of say, temperature and overall energy. A single particle in a box may have a restricted configuration, but the atoms in my body and your body can be in very many different configurations and still be at the same temperature. So there's a lot of entropy associated with a macroscopic object. And the more, if you wish, the more internal possibilities that a system has to explore within the confines of some external parameter that's restricting it, like the total energy of the system, or its heat content, or some other aspect, or its volume, the more internal configurations the system has to explore, the bigger its entropy.
So I was thinking, for example, I'll give you a narrative example. It's actually apropos because my car did break down today, but when you're in your car and you're driving along and everything is going according to your desires and expectations, then you're generally in a low anxiety state. But then imagine that the car emits an unexpected noise and starts to buck. Now, one of the things I've proposed is that at that point you're actually no longer in a car, and that's why you get upset, because the car is actually functionally described as a category. The car is something that gets you from point A to B. And as long as it's performing that function, then that category was a very low resolution category. That category suffices, but as soon as something goes wrong, the same thing happens when your computer does something you don't want it to. There's so many different states that thing could be in that your body signals that emergent complexity, and it signals the fact that you can no longer compute the cost of being where you are. And, there's fantasies that are associated with that seem like attempts to map it, right? It's like, this could be wrong, this could be wrong. I might go to a crooked mechanic, I might get ripped off, I might not be able to fix this car, maybe I can't afford it, I won't get to work. Like the whole panoply of possibility expands very, very suddenly, and that produces an intense physiological response, which it should do. I mean, we should have physiological responses to fundamental physical realities.
We should. Most of us ignore them, and I think that's the point. The physiological response you're talking about is real, but in fact, when the car is operating well, all of those possibilities also exist. You just block them out of your mind. I mean,
that's an interesting thing too, right? But it's appropriate in some sense. We were trying to understand to some degree the conditions under which it's appropriate to block them out of your mind, and it's something like, as long as your predictions, but they're based on your desires, but we won't get into that. As long as your predictions match the ongoing flow of events, then you can take all of the presuppositions that order things for granted. I mean, I agree with you completely that all those things could be going wrong at any time. But the same is true of the complexity of your body, right? I mean, it isn't necessarily the case that just because you feel good right now, you're going to feel good the next moment. And there's an endless number of things that can go wrong, but it's also not helpful to be aware of all of those possibilities if they're not likely to happen. So it isn't exactly that you ignore them, it's that you assume their functional significance is zero as long as your plan is operative.
And but I think, it goes back to maybe human reason being the slave of passion. I think the point is you're right, it's not worthwhile assuming all the negative things that can happen. If it did, you wouldn't do anything, right? If you want to take any action, if you assume all the negative things that could result from it, you probably wouldn't act at all. One of the things that I think we do, and one of the problems we have as a society, in fact, that's related to even my last book, is that we tend, one of the things that science does, which I think is so useful, is it quantifies uncertainty. Uncertainty is a central part of science, and too often, journalists and other people talk about uncertainty as if it's a bad thing. In science, it's actually a very good thing because we can say, we can define, we can quantitatively say how accurate our result is or how likely or unlikely a bunch of possibilities are. I think psychologically,
and there I would say that's an anxiety reduction phenomenon. I mean, when you enter into a contract, you're doing that with someone too, because what you're saying is, well, I could be any number of possibilities, but contractually I'll limit myself to this manifestation, and that can make you calm, and it can make us able to cooperate. And so I think that it's not only a scientific theory that provides that function, it's a science would be a subset of practical theory, and practical theories, they're very useful exactly for that reason.
They are, but I personally think more people could be. I think it would be it would help people if they accepted the existence of uncertainty in a more open way. I think people are afraid of uncertainty, and I think if we, including death and the universe and all sorts of other things we may talk about, and I think accepting it as a realistic likelihood is a healthy thing because, again, it relates to some extent to some of the, I think, social problems that are happening now of kids being coddled. If you accept that bad things can happen, then when you do it, as part of living, then you won't be so anxious when they do, I think. I mean, you won't be so fearful of that. Okay, yeah, your car can break down, but the world isn't over. There's a whole series of other activities you can take place that will allow the world to go on, that will allow you to continue to function. But recognizing at some level a spectrum of possibilities in advance, in my opinion, and I'm not a psychologist, but in my opinion, certainly personally, I find it psychologically helpful. Yeah.
Well, it is definitely the case that that's promoted among psychologists and behavioral psychologists. You may imagine that one thing you want is a theoretical configuration that encapsulates uncertainty. That's a belief system, let's say, and you measure it by its functional utility. Does it allow you to acquire what you desire when you act it out? But you need a codicil along with that, which is, well, what do you do when your theory goes wrong? And one of the answers that's being provided to that question from the behavioral perspective, it's coded in narrative as well, though, is approach uncertainty voluntarily and cautiously. Don't avoid it. And that triggers another mechanism, which is the capacity to explore, to generate new theories, to select among them, especially in collaboration with other people, and to regenerate your pre-existing models. So you need the model, and you need a system for updating the model. And you see that expressed in pretty formally in science, in the scientific technique.
It's a central part of the scientific method, and I would also argue in business and many other areas of human activity that people don't realize. What I try and convince people of, they don't realize that scientists actually really like to be wrong. At least, and whether personally they do is a different question, but the process of science, it's exciting to be wrong because it means there's more to learn, first of all. And it means you discovered something. It often means you've discovered something. And one of the things, I was chairman of the physics department for a long time, and then we started a program, a master's degree in physics entrepreneurship, which the business school dean said was an oxymoron, but I don't think so, because I think scientists and business people are very similar, because often what I realize we don't do well enough for children, for students or whatever, is teach them how to fail effectively. We give them problem sets that they're guaranteed that have direct answers and they get the correct answer. We even give them PhDs where they're more or less guaranteed to at least come to some conclusion. But in the real world of research and business and many other things, you may find that you have to learn how, well, the question I was asking was really not a good question. How can I use what I've already accumulated to nevertheless provide me something useful, maybe ask a different question and go around? And so I think that training to fail effectively, namely to find that the thing you were trying to show is wrong, but nevertheless the process by which you discover that is very useful and can be useful somewhere else is a central part of science, but I actually think it's probably very useful again in real life, and I think most business people, when I learned about entrepreneurs, I asked the physicists who become entrepreneurs what they hadn't learned, and it was just that, how to fail effectively, because often startups, well-known entrepreneurs have had 3 or 4 or 5 startups that have failed before they get to where they're going. And I think, but it's the same of any researcher. in your research, I'm sure, as in mine, there have been many false starts, many roadblocks, many times when you just discover, hey, this problem is really not amenable to being solved, but maybe I can ask a slightly different question. So I think being aware, being less anxious of the fact that your planned trajectory is not going to go where you took it is actually a wonderful part of life. As a scientist, I often say when I write, you probably had this problem too, you write grant proposals and you write some fiction of what you're going to be studying in 3 years. And I always say that if I'm really doing what I thought I was going to be doing in 3 years, it's pretty boring, because what I really hope will happen is I'll be looking at something completely different, because some new discovery will have come up, either from the outside world of experiment or from something I'm doing.
Well, is it reasonable to ask you, can you remember times when that specifically happened in your career, where you had to reconfigure and you discovered something that was worthwhile as a consequence of it?
Oh yeah, it's hard to imagine when it hasn't happened in some sense. I think let me give you an example. The one you mentioned, the discovery that the energy of empty space is the dominant energy of the universe. I was studying cosmology, and of course, and the amazing thing about cosmology is it's over the last 30 years turned from, or 40 years, from an art to a science. I think people used to say cosmologists were never right but never in doubt. But wonderfully, what's happened, because science is an empirical discipline, is that whole new data sets were coming on, new machines and new telescopes, which were allowing you to make precision tests of the universe and therefore derive models that could be disproved, which is really the central part of science. And when I was trying to understand that, and I've been working on the subject of dark matter for many years, how to detect it, the fact that most of the mass in our galaxy, all galaxies, appears to not shine. And now we're reasonably certain it's made of some elementary particle that's different than the particles that make you and I up. It's a fascinating thing, and I've spent a lot of my career thinking about it. But one of the reasons we became confident that that was the case, that these particles, this dark matter was not made of protons and neutrons and the same stuff as you and I, was because we built cosmological models, and we found that if this dark matter was just snowballs or something that you couldn't see, then plugging them into our models, you couldn't get a universe that looked like what we look like today, starting from a hot Big Bang. You couldn't form galaxies. There wasn't enough time. And so dark matter, it turns out if dark matter doesn't interact with light, it's easier for it to collapse early on in the history of the universe, and that gives a jump start to galaxies and et cetera, et cetera, et cetera. So we're trying to come up with a model that really was in agreement with observation. The problem was the observations ultimately weren't in agreement with that model. And so the question then becomes, what do you do? And so I was reasonably convinced at the time that the reason that was the case is some of the observations are wrong, which is also something very important to realize in science, is that if there are many different observations, likely some of them are wrong. And again, too often journalists don't hit on that fact. They concentrate on this one exciting observation, which is likely to be wrong, and when it's later on shown to be wrong, they never report on it. And that's part of the problem. But so I basically was convinced that some of these key observations were wrong because they're very difficult. And so, somewhat heretically, I made this proposal. I looked with, it was a colleague of mine at University of Chicago, and I spent a year or two looking at all the data and saying, how could it be consistent with dark matter and what would be required? And the answer was, if none of the observations are wrong, then it looks to us, it looked to me at the time, like you'd have to have most of the energy in the universe reside in literally nothing, because observations weren't consistent with the picture otherwise. And I was convinced at the time that the reason I was doing that was just so that people could focus on which observations were wrong. Mm-hmm. And so they could see that, because the proposition was so ridiculous that empty space actually weighs something. You get rid of all the particles and radiation, everything that's there, and yet empty space weighs something. That seems so crazy that surely it's wrong. And there must
it seems to violate the very presupposition that enables us to identify mass. I mean, mass by definition appears to be something.
Well, mass is different than energy, okay? And energy, And if you put energy in empty space, and Einstein realized this, if you put energy in empty space, it behaves very differently than it does if you put energy in matter, like particles. In fact, what general relativity tells us is that mass isn't the key part that produces gravity, it's energy. So there's this relationship between energy and gravity. And energy in different forms produces different types of gravitational attraction. And in fact, that's relevant to the history of the universe. Early on in the history of the universe, most of the energy in the universe resided in radiation, hot stuff like particles of light moving at the speed of light. They gravitate very differently than if most of the energy in the universe resides in planets or galaxies, matter. That's the same. And so the expansion of the universe, which is gravity's response to the presence of energy, is different early on in the history of the universe when it's dominated by radiation.
Is that one of the things that contributes to the rapid inflation at the beginning?
Well, in fact, it's not quite. You're almost there. It turns out rapid inflation happens if at very early times in the history of the universe, empty space gets energy. Because it turns out if for some reason empty space gets stuck, somehow it possesses energy, even if in the case of inflation, eventually it's going to release it in a hot Big Bang. If that energy gets stuck in empty space carries with it this property we call energy. That energy is gravitationally repulsive, not attractive. That's the key difference between energy when you put it in matter and when you put it in nothing.
Okay, so you said a couple of things that I want to follow up on. Okay, so and maybe you can take us back. So you said in the last 25 years that cosmology has transformed itself from an art to a science. And so maybe you could tell us the science. Let's go back to the beginning. Sure. 14 billion years and walk through it. And because I'm sure that, well, I certainly don't understand the role of dark matter or anything about dark matter. And I kind of had some sense of what the current cosmological theories were 20 years ago, but I really don't know what they are now. So let's go back 14 billion years and start at the beginning, if you don't mind.
Sure, we'll try and spend less than 14 billion years describing it. But okay. By the way, before we get there, let me just end the last story by saying we made this crazy proposal because we were sure the experiments were wrong. It turned out the experiments were right and the craziness was true. And no one was more surprised by it than me that this proposal that the energy of empty space it dominates the energy of the universe was right. It was just incredibly surprising. It was so surprising that eventually the observers who confirmed that fact won the Nobel Prize 11 years later.
Well, in your book, The Greatest Story Ever Told So Far, you document a large number of cases where theoretical physicists were driven to posit something they regarded as completely absurd because it seemed to fit the data, assuming that something was wrong and were later shown to be right, even though they wouldn't necessarily accept that themselves.
Exactly. In fact, one of the founders of quantum mechanics, Dirac, who's a very interesting man psychologically and other things, once said his equation was smarter than he was because he developed this equation and he predicted this whole nature antimatter, and he didn't believe it, and he said it was the equation and it turned out to be true. But anyway, let's go back to the beginning, and when we go back to the beginning, this is an important difference between, in my mind, science and, say, religion. When I go back to the beginning, I go back to as far as I can extrapolate my understanding of the laws of physics back. Before that, almost anything goes. And science, we can make, and part of my job as a theoretical physicist was make speculations, but to recognize that they were just that and look for signatures that might suggest whether those speculations are right or wrong. So, for example, I actually wrote a book called Atom, which takes you back to for an individual oxygen atom from the beginning of the universe to the end, one that's in your glass of water that you're drinking right now or during this podcast. And I took it back to not t equals 0 because literally we don't know what happened at t equals 0 because the laws of physics, as we understand them, break down. Because the universe, if we extrapolate it back, our universe becomes infinitely dense. And that seems crazy, and the laws of gravity don't work with quantum mechanics, so we really can talk a lot about it, but it's not more than talk, in my opinion, right now. But very shortly thereafter, after that time, there's no reason to suspect that the current laws of physics don't describe what happened in the history of the universe. And again,
so as soon as it comes into being, the laws come into being as well.
Yeah, well, in fact, in the universe universe or nothing, I suggested that's certainly a possibility. Maybe they pre-existed, maybe they don't. Those are metaphysical questions. But what I did show in that book, which is fascinating to me, and the fact that 30 years ago we wouldn't have even been able to ask the question, much less answer it, is that it's quite likely that our universe could and did spontaneously arise out of nothing, no space, no time, and maybe no laws. And if you ask, what would be the properties of a universe today, 14 billion years later, that arose from nothing spontaneously without any supernatural shenanigans, the properties of that universe would be precisely the properties of the universe we observe. Now, that doesn't prove that's the case. That just makes it plausible. But to me, that's a fascinating thing. And again, 30 years ago, we didn't have the tools to even, in some sense, ask that question. But
we're still estimating the birth of about 14 billion years ago?
13.8. Yeah. Now, if you actually look at the numbers, which we can measure, we now know that number, 13.8, to an accuracy of, plus or minus of maybe a few 100 million years or two. 13.75, I think, is the most recent number. And it's amazing. The fact that you can get beyond one decimal place in cosmology is just remarkable. And it really is a testament to the developments. When I was even a young assistant professor at Yale, I remember talking to an older colleague who said that nature would always conspire so that we could never measure the fundamental quantities of the universe better than within a factor of 2. Because that had always been the case up to that point. Every time someone claimed to have a better measurement, you'd go out and look at astrophysical uncertainties and realize it was wrong. And now we're talking about measuring things to 4 or 5 or 6 decimal places. It's really a transformation and one we're celebrating, which is what I tried to do in that book. But the early picture, the fact that we evolved from a Big Bang is not in dispute. Let me make that clear. The Big Bang happened just like evolution happened, and the Earth is round, and all the other things we know. There's no doubt that that the early history of the universe was a hot Big Bang. Now, and in fact, everything we now see, all the galaxies we now see, and all the particles in those galaxies, the 100 billion stars in each galaxy, the 100 billion galaxies, all of that material was contained in a region smaller than the size of a single atom. And that's just so.
Let me ask you a question about that.
Sure.
I mean, is it reasonable to conceptualize something like that as having a size? Because we're considering size within the universe, and it's almost, when you say that the universe at the beginning had a size, it's like it was an object in a universe that had a size. But
it's a really good question, and I should be clearer in my language. The universe could be infinite. I want to ask, as a physicist, and Wheeler would have liked this, Einstein certainly, that operational questions. I don't know how big the universe is, whether it's infinite or not, but what I do know is, how big is the visible universe? So if I ask you, how big was the region which now comprises the visible universe today at an earlier time, that has a good, that's well defined. That region the size of an atom could have existed in a universe which was infinite even then. It could have been an infinitely dense universe that was infinitely big. Okay? So all we can ask, and this is really a big change also from when I was a student, because we used to, when I was a kid or when I was even a student, we talk about universe, and universe would mean everything. A kind of ill-defined quantity, everything. What the heck is everything? Now we're much more well-defined. We say our universe, a good definition of our universe is that region with which we could have interacted in the past and with which we will be able to interact into the future, even if the future is infinitely long. And that may not be everything, right? That could be just a small region of a much bigger thing, which we now call a multiverse. So it's reasonable to describe our universe as that region into which we could have had causal contact, namely which cause could have produced effect, right? And if there's any region outside of it which we can never affect or be affected by, that might as well not be considered part of our universe.
That
right?
distance, that causally interactable distance, that's defined or limited by the speed of light?
The speed of light and the age of the universe. So, for example, in the early history of the universe, that's called the horizon. In analogy with the Earth, when you look out at the Earth, you can, when it curves, you can only see out to a certain distance. And we call the causal horizon that region with which light could have traveled to interact with us since the beginning of time. And
obviously it's the universe as far as we're concerned, because nothing outside of that can affect us in any way.
Exactly. So operationally, it's a much better definition of the universe to be that which we can be causally affected by. And so, and because that changes with time. That's what is our observable universe changes with time, and we'll get to it because things have changed a lot in those ways.
Does that mean that the universe that causally affects us we're at the center of it?
No. Well, actually, yes and no. We're always at the center of our own universe, right? I mean, psychologically.
Because of the causality argument that you just laid out, it seems to imply that directly. Because
it certainly does in the sense that if you want to think of it, and this is one of the confusions and many confusions which I may add to during this podcast, but we'll try not to, is that when we look out at this thing called the cosmic microwave background radiation, it's a residual radiation left over from the hot Big Bang. And it comes from a sphere, if you wish, that's located with us at the center. Because it early on in the history of the universe, when it was hot and dense, light interacted with matter, and basically it followed a random walk. It wasn't free to travel because all the universe was charged and light would interact and bounce off things. But at a certain point, when the universe was about 300,000 years old, matter became neutral. Protons captured electrons from hydrogen for the most part. And neutral matter doesn't interact with light as strongly as charged particles. And that meant that radiation, which was kind of trapped early on when the universe was 200,000 years old, could suddenly travel freely through the universe without really interacting. And when we look out, basically we see space and the light, could travel. But if we're looking back further in time when we look out, and if we look out in that direction, back to a time when the universe was 300,000 years old, we're kind of sort of going to see a wall, if you wish, because we can't see before that time because the light, couldn't have propagated out, just like it can't propagate out through a wall. Only from the surface of the wall can we see it. And of course, so when I look at the microwave background from Earth, I'm looking, if you wish, at the sphere located almost 13, well, actually it's, because of the expansion of the universe, it's about 26 billion light years in each direction because the universe has expanded during the time that the light has been traveling. But don't worry about that complexity. We're looking at a sphere located a certain, let's say, 20 billion light years away from us in all directions, and we literally can't see beyond that. But the sphere we're looking at depends upon where we are, so that if we were doing the same experiment on an intelligent species in another galaxy located 100 million light years away, literally the cosmic microwave background that they would see would be slightly different, because it'd be a sphere centered on a different place. And that's why, actually, the predictions we can make, in some sense, as cosmologists, are somewhat statistical. Because we're talking about a thermal distribution and galaxies and lots of disorder. And so the picture, and we've taken pictures of the microwave background, it's won at least 2 Nobel Prizes for those pictures. The picture that we see has statistical properties which would be identical to those observed by another observer 100 million light years away, but the specifics, the hot spots and the cold spots would be different, because they'd be looking at a different slice of a statistical distribution.
Sure. Okay. So that does, correct me if I'm wrong, that does seem to imply that, so the universe is a globe around us, let's say.
Our visible universe.
A visible universe. Sorry, I want to be precise with my words too. And so I move halfway across the universe, and the globe is still there, but now it's shifted that far. And so then I can move another halfway, and it would shift again. So this globe moves with the observer, so to speak. And that certainly seems to imply that it extends beyond the globe that we see. Because if you move, it moves. So, and
exactly, and it wouldn't if there was some edge, but there's no evidence of any edge. Okay, I think that the point is that even before the weirdness of empty space and inflation, it was recognized that the part of the universe we see is unlikely to be everything there is. We're limited in what we can see because of what's seeable. Just like being on Earth.
And it's limited because of the speed of light and the age of the universe, but also because of the way the universe was constituted in its early stages.
And the way it's expanded ever since. Let me throw in a wrinkle. If that was clear, now let me muddy it. Okay, because it used to be, again, sensible, even in my early career as a scientist, that we'd assume the older the universe, the longer we live, the older the universe is, the more we'll be able to see. expansion was slowing down, and therefore the longer we wait, the more we'll see, because light from further and further objects can get to us. What's really crazy now is because we recognize that apparently empty space is dominating the energy of the universe, that's causing the universe to expand ever faster and faster and faster. And what it means is there are parts of the universe that are literally escaping from our sight. There are parts of the universe that we will never be able to see, and moreover, even more so, there are parts of our universe that we could see now that if we were a civilization that developed 5 billion years from now and built telescopes, that we couldn't see then. Because regions of the universe are eventually moving away from us faster than the speed of light and are now invisible. So the longer we wait, the less we'll see, because more and more galaxies will be literally disappearing behind the horizon the longer we wait. I wrote some papers about that, and once a Scientific American article, and I think some of my books, that eventually the far future of the universe, I know we said we'd start in the past, but the far future is kind of poetic, because up till about 1925, the picture of the universe was quite natural based on observation. One galaxy, we saw one galaxy, the Milky Way galaxy, okay? And beyond that, it was assumed to be eternal, empty, dark space that just was static. And Edwin Hubble, who was famous for discovering the universe was expanding, did something before that. In 1925, he first realized that, in fact, there were other galaxies, that these things called nebulae in our galaxy with the new 100-inch telescope at Mount Wilson could be discerned and be seen as other island universes. So already that was a revolution in our picture of the universe. Suddenly, our galaxy wasn't all there was. There were other galaxies. And then, of course, later on, he discovered the expansion of the universe. The interesting thing is that observers who evolve, and there'll still be stars in, say, even up to 10 trillion years from now, there'll probably still be stars in existence, and you can imagine planets around those stars and intelligent life evolving on those planets. And astronomers will look out from our galaxy. At that time, it'll be a very different looking galaxy because the Andromeda galaxy will have collided with it and all sorts of things will happen. But they'd look out, and the interesting thing is all other galaxies would have disappeared behind the horizon. And so observers 10 trillion years from now will think they live in the universe we thought we lived in 1925, a universe with one galaxy, and there'll be no evidence that the universe is expanding, no direct evidence, because the galaxies that are now markers that we can measure their motion away from us, they'll have disappeared. And even, it turns out, the cosmic microwave background will have become invisible by that time, which is another bit of evidence for the Big Bang. And while some really smart scientists may come up with some pictures to say, well, really, I can understand what we're seeing if we assume our universe began at the Big Bang, observationally, basically, all the current observational markers of an expanding universe will have disappeared. And poetically, in the far future, they'll think we lived in the mistaken universe we thought we lived in 1925, because, again, it's kind of interesting. Conventional wisdom in 1925 scientifically was that the universe was static and eternal. And you may know that it was actually a Jesuit priest who was also a physicist who first really suggested the Big Bang. And when it was later shown to be true, for a while the Catholic Church got quite excited because they argued that here was observational evidence that there was a beginning to the universe, as they'd been arguing. It doesn't provide any such evidence for the universe they discussed. But it was an interesting fact that science, the model was that the universe was more or less static and eternal on large scales, and it was completely wrong. And you might say, and this is where people often write to me and say, well, how do we know our current model isn't completely wrong? That we had a Big Bang. And the answer is, then there was no data, basically. And, one of the biggest misconceptions about science and scientific revolutions, in particular revolutions in physics, is the misconception that scientific revolutions do away with everything that went before them. Just like Piagetian revolutions, right? Yeah, in fact, I would argue that even political revolutions never do away with everything that went before them. But in this case, they certainly don't. What survived the test of experiment before that revolution remains completely true. Newton's laws of gravity and motion may have been subsumed in quantum mechanics or relativity, but if I hold a ball up now, it'll fall just as well as described. And I can describe a cannonball. I can even, for the most part, calculate how astronauts are going to go to orbit without needing anything
Yeah,
beyond
the developmental psychologist Piaget studied Kuhn's scientific revolutions, and his objection essentially was that when a child undergoes a cognitive restructuring, the new structure incorporates all of the knowledge of the old one plus some new knowledge. So it can be revolutionary, but it still subsumes it.
Exactly, and that's exactly what happens in science. So it's not as, so we have a lot of data with which we can test ideas, and I'm certain that there's much more we don't know about the universe than we do. What people don't realize is, or don't give credit to, is that there's a lot we do understand. And any new picture, a new understanding, will not be able to disagree with the observational evidence that the universe is expanding, that there's a hot cosmic background, all the things we now have discovered that we didn't know about in 1925. And so whatever our picture is of the beginning of time or the end of time in 100 years may be very different, but we know we're not going to ever say that the age of the universe is no longer 13.7 billion years old. That's going to remain true. What happened at the beginning could be completely revolutionarily different. It would happen, if you want to think about before the beginning, if there even makes sense to describe it before, and it may not make sense because time itself could have originated.
Well, let me ask you about that for a second.
Sure,
okay?
sure.
Well, I thought a lot about time a long time ago, and it struck me that time is we mark time by change, and so then I thought, well, why not dispense with time as a concept if we mark it by change? Time is average change. If nothing changes, there's no time. So if there's nothing happening, there's no time. There's no before that time. There's an event, and then if there's no event till the next event, there's no duration between those two things if there's only that event and the next event. So, I mean, is there any reason to assume that there's anything about time that is independent of change?
Well, obviously it's a very deep question. And a lot of people spend a lot of time on time, I think far too much time talking about time. In physics, time and space are not different. They're both, if you wish, parameters that simply describe when events happen and where they happen. And that's it. And it turns out that that's the playing field on which the laws of nature play out. The playing field happens to be in space-time. And time is no different than space in principle, except in fact, in practice, time seems very different than space. We can go backwards in space, but it's not clear we can go backwards in time. And that's causing a lot of people, a lot of philosophers and then physicists, a lot of problems and a lot of mental gymnastics. But even, but you could argue that time is a parameter, and I could replace that parameter by some other parameter that is equivalent to time. And you could say that that parameter was change, like the parameter you talked about. And then if there's no change, then you'd say, okay, well that's it. You could say that parameter isn't changing, and
there's changes happening all the time at the microscopic level, right? I mean, there's an indefinite number of changes, and so statistically, you can extract out an average from that, and you can experience that as duration, and you can define that as time. But if there isn't anything there except one event and then the next event, well, that's it. There's no time there. There's an event and then there's the next event.
Well, that's where I disagree with you. I guess that's why you're finding it. Because if nothing is happening, literally if nothing's happening, then time is an irrelevant concept. But to some extent is space, and to some extent is physics. Because really what we're interested in is describing the process of events, in particular the prediction of events. And that process of going from event to event is parameterized by a useful quantity called time. But if nothing's happening, you're right, it's completely arbitrary, but then we wouldn't be having this conversation because nothing would be happening. So in a universe in which nothing was happening, there'd be no time, but there'd be no reason to talk about it either.
All right, so back to the beginning. Now, my understanding, I don't understand why there is something once something is created, because as far as I can tell, and I don't think I was disabused of this notion I finished reading The Greatest Story Ever Told so far this week. Why weren't there equal amounts of matter and antimatter produced at the beginning, so they just disappeared? Everything just disappeared.
That's a good question. And we assume
Does that have anything to do with uncertainty? With the fact that there isn't, I'm wondering if there wasn't equal numbers produced.
Well, look, the point is that we don't have an answer to that question. And by the way, I think that's really important as a scientist. And too few people, journalists always want answers, and people are always disappointed when they say, we don't know. But I think it's probably one of the most important things that we and parents and teachers should get more used to saying, because it means there's more to discover, and that's wonderful. So the answer is we really don't. It's one of the biggest questions that's really provoked much of the field of research that I've been involved in since I was a student. I remember Stephen Weinberg wrote about it when I was a graduate student and got me interested in that whole subject. We now know that we live in a universe that's made of matter. And we try and measure antimatter, and there's minuscule amounts of it. And we think most of it's caused by high-energy collisions between particles and causing rays. As far as we can see, and there are real tests we can do. For a while, people thought maybe we lived in a universe that had equal amounts of matter and antimatter, and they were separated. There were matter regions and antimatter regions. But it turns out there are tests you can do to test that. And all of those tests demonstrate that, as far as we can tell, that that the universe is made of matter, not antimatter. Which again is arbitrary, because of course if we live in a universe made of antimatter, we'd call it matter. And and there'd be anti-lovers living sitting anti-cars, making anti-love and all the rest. It wouldn't be different for the most part. But the paradox here is, at early times, the universe is very, very hot. And when it's so hot, one of the central parts of relativity is that energy can turn into matter and matter can turn into energy. So particles of light with enough energy can collide together and produce particles of matter. Okay? But when they do that, if they have enough energy, then since antimatter and matter have exactly the same mass, particles that collide will produce equal amounts of matter and antimatter. If two photons at very high energy, and they don't collide very easily, but if they do, they'll produce particles and antiparticles equal numbers. Partly because of the conservation of charge, right? The photon doesn't have any charge, and therefore whatever comes out of the collision has to have no charge. So if it produces an electron, it'll have to have a positron, the opposite. So all those interactions, elementary particle interactions, don't really distinguish between matter and antimatter. And therefore, at very early times, if you were a creator, if you were creating a universe, and it was very hot and dense, the most reasonable thing would be for it to have equal parts of matter and antimatter. Okay? But somehow, so that's the reasonable assumption for the beginning of time, that the universe had equal amounts of matter and antimatter in a very hot, dense plasma. How do we get to a universe that just has matter? Well, that is the interesting question. And it turns out, by the way, and I know you're interested in what you would call Soviet things, like the art and everything else, and Alexander Solzhenitsyn.
I collect it. I don't know if I like it. But I do collect it. But Andrei Sakharov was a very famous physicist, who was actually probably the father of the hydrogen bomb. But he was also, as you know, won the Nobel Peace Prize because he became a dissident. Interestingly enough, one of his major, in retrospect, one of his major contributions to science was he actually asked in, I think it was 1967, well before any of the physics actually allowed any of it, he came up with 3 criteria by which a universe that started out with equal amounts of matter and antimatter could evolve into a universe which just had matter. They're called the Sakharov conditions. And there are 3 of them. One is that you have to depart from thermal equilibrium. Because if you're in thermal equilibrium, everything remains the same. So nothing's going to happen, right? Okay? Thermal equilibrium, like the air in this room. Okay, so there's a place where uncertainty seems to be relevant, because if the principle of uncertainty holds, you wouldn't have thermal equilibrium. You'd have unavoidable variation.
Well, no, but you have you do have local in thermal equilibrium in this room, there's local variations. The thing about thermal equilibrium is, and you're right, in fact, what you just said there is right. Normally we talk about thermal equilibrium being a global thing, but we can also talk about microscopic equilibrium, and there are variations. But what happens is that in thermal equilibrium, one particle turns another particle, big collision, but an equal number of collisions happen in the opposite direction. So there's lots of things happening, but they're all happening in equal opposite ways, so that no global properties are changing. Okay? Okay, and certainly the amount of matter in the universe is a global property. Okay, so thermal equilibrium. Okay, the second is that you have to have some physical process that tells the difference between particles of matter and antimatter. Okay, because if the physical processes don't tell the difference, then nothing is going to start a situation that has equal numbers and change it to a situation that has unequal numbers. Okay, this property is called, it happens to be the laws of physics that tell you matter and antimatter. The laws of physics are the same for matter and antimatter, are related to two symmetries of nature, something called charge conjugation invariance, which tells you that positive and negative, there's no difference in positive and negative, it's just an arbitrary thing. And it turns out there's no difference between left and right. Okay? If the laws of physics at a microscopic level obey both of those properties, then the laws of physics will not distinguish between matter and antimatter. Only if that's violated, that's called CP, charge and parity. Only if CP is violated can you, by some microscopic physical law, can you evolve from a system with an equal number of particles and antiparticles to one that has one. And the third is something called, we call it baryon number non-conservation, but basically, matter is made of protons, okay? And electrons are obviously protons and electrons make up atoms, but electrons are very little mass. Most of the mass in your body is protons and neutrons. They're called baryons, okay? And clearly, if you want to end up with a universe full of protons and neutrons, and more protons and neutrons, if you wish, than antiprotons and antineutrons, then there has to be some process that makes protons when there weren't protons to begin with. So those so this thermal equilibrium, CP violation of thermal equilibrium, violation of CP invariance, and some process that violates what are called baryon number. Okay, and he wrote those down. And what's amazing is at the time he wrote them down, the laws of physics obeyed thermal equilibrium, the universe obeyed CP, and obeyed baryon number. So there's no evidence that you could ever do that. And what's been remarkable is that over the last 50 years or so, is as we've studied the microscopic laws of physics, we've discovered both that CP is violated by microscopic laws, and we've discovered processes that could have happened in the early universe that would violate that thermal equilibrium, that nice general, what you call adiabatic expansion of the universe. There could have been abrupt processes during which the universe departed from thermal equilibrium by natural processes that we could describe. In fact, we know there were some of them. We know, if you read my book, we know, for example, now that the two forces of nature, electromagnetism and the weak interaction, that now appear very different, early on in the history of the universe actually represented two different sides of the same coin. They were really part of a single, more unified force. Okay? And the point where the universe cooled down enough so that suddenly electromagnetism began to behave differently than the weak interaction, as the universe cooled down and things suddenly began to behave differently, that's what we call a phase transition. And phase transitions are places where you could depart from thermal equilibrium, right? I don't know if I use the example in the book, but I grew up in Canada, so the example is beer. But if you have a party, a beer party, and you forget to put beer in the refrigerator, you put it in the freezer, and then you forget that you put it in the freezer, and the next day you take it out of the freezer and it's frozen solid. I mean, it's not frozen solid; it's still liquid. But you take off the top, and suddenly it freezes instantaneously, and the bottle breaks. That's a phase transition. Because when the beer was being held under high pressure, it wasn't at a low temperature. It wasn't really in thermal equilibrium. When you opened it up, then it could suddenly go into thermal equilibrium, and the preferred state to be in thermal equilibrium was ice. And suddenly, boom, it breaks. So thermal equilibrium. So phase transitions are points where you can depart from thermal equilibrium momentarily before the transition completes.
There's a theoretical explanation for how the antimatter matter.
The point is there's no one theoretical explanation, but we now know all the parts, the Sakharov exist, but we don't have any good model that puts them all together. We thought we did in the 1980s when I was at Harvard. We thought we we thought there were, even before that, when I was doing my PhD at MIT, we thought there's a model called grand unification. It all looked like it was falling together, and we thought we had the answer to everything, and it turned out the experiments have told us that those pictures are not quite right. There's a host of possible ways of starting out with a universe that has equal amounts of matter and antimatter, and ending up with a universe that has unequal amounts, but we don't know if any of the proposals that we've now made are correct. And if history is any guide, my feeling always is the most likely answer is one we don't yet have. I mean, I've written papers, lots of models that can make that happen, but nature probably isn't smart enough to use any of the models that I've written down, and I suspect it. But so there are lots of ways, but what's neat is that experiments have shown, and that's what's important. It's not just theoretical, mumblings of physicists who like to have nothing better to do. Experiments have shown all the components of the Sakharov requirements for generating matter, a universe that had an asymmetry, are possible in nature and are suggested. I should be a little more careful. We know phase transitions happen in the early universe. We know CP is violated. Baryon number, we don't know to be violated. But all of our models that extend what's called the standard model of particle physics naturally produce at very early times models where baryon number is violated. So it's not implausible. It's certainly not implausible. And so all those things exist. And our current picture is really quite, having said all of that, that's complicated. The current picture that is a little simple, and it's really remarkable. It says that what happened is there were equal amounts of matter and antimatter, and a physical process happened sometime between the Big Bang and the time when the universe was about a millionth of a second old that caused a very slight excess, 1 part in a billion, more particles of matter than antimatter. And that's all you need. You might say, why is that the case? Because we now live in a universe that's just matter. Well, if I have let's say there's 1 billion and 1 particles of matter, and a billion particles of antimatter, what will happen as the universe evolves? The particles of matter will annihilate with the particles of antimatter, producing radiation, but there'll be one leftover particle that couldn't find the particle of antimatter to annihilate. So what you'd expect is roughly 1 billion particles of radiation in the universe for every particle of matter. And when we look out, that's exactly what we see. The cosmic microwave background contains roughly 1 billion to 10 billion photons going throughout all of space for every proton in the universe. So in fact, while we think we really live in a universe of matter, what we really live is a universe that's mostly radiation, polluted by a little teeny bit of matter, 1 part in a billion, but that teeny bit of matter is enough to make all of the stars and galaxies and you and I. So, one of the things that I'd like to think of in physics is it makes us more and more insignificant as human beings in a cosmic sense. We realize we used to think we're the center of the universe, we're the center of the sun, the sun went around us. It's been a series of these kind of Copernican revolutions where the Earth isn't the center of our solar system, but the sun is at the center of our galaxy, but our galaxy is at the center of a cluster of galaxies, and our cluster of galaxies is at the center of the universe. And now we find that most of the particles in the universe aren't even made of the same stuff as we are. So it pushes us more and more to feeling marginal. And I find that, and a lot of people say, well, that should make us feel sad. But to me, it makes me feel more precious rather than less precious. It's like, obviously, we're getting into the realm of psychology, but my psychological response is, hey, the fact that the universe is accidental as far as I can see and was created without any supernatural shenanigans, the fact that we're cosmically irrelevant, the fact that the universe is going to go on without us, all that doesn't make me feel sad. It makes me feel I should enjoy my brief moment of the sun. I should enjoy my brief, 40 and 10 or hopefully more and years. And it makes this accident of life on Earth remarkable that evolution has endowed us with a consciousness so you and I can have these discussions. So I don't find the pointlessness of the universe to be depressing. I find it rather the opposite. And I often, and this may be an area we disagree in, I don't know, but one of the bits of semantics that I've tried to fight is this notion of loss of faith. Like losing your faith is a loss. But to me, losing my faith in those fairy tales, at least, or those incorrect explanations, is not a loss, it's a gain. And using that terminology makes it seem like people always write to me. I now recognize, that I don't believe the Bible stories, but what am I to do? I mean, how can I deal with this loss? And I think they're conditioned to feel like they have a loss. I don't think so. I think you can psychologically create a picture where you don't feel that's a loss. You feel, in fact, you've gained something. And actually, it's the way I feel about many things in life when I'm being well-adjusted, which is a small percentage of the time, to be clear. When I have a loss, I often reflect on it afterwards and realize, in fact, I've gained. That what seemed to be a traumatic experience, in the end, produced something which is much more valuable. And of course, it's a rationalization, probably. But it allows me to deal with those things anyway. Anyway, I look at psychology. I've done mental psychology for discussion.
I'm tempted to take it in that direction, but I think I'm going to continue